Hi everyone. In this video we're going to talk about direction fields. So first let's mention the nature of a solution. So a solution can tell us about a value at a certain point. It can tell us about intervals of increasing and decreasing. It can tell us about the location of maximum and minimum values and other things. So many differential equations can't actually be solved analytically. And so graphical and numerical methods help us analyze behavior of differential equations. So that's what we're going to be talking about in this section. We're going to talk about a graphical method. And so a direction field is a plot of short line segments drawn at various points in our xy plane that show the slope of the solution curve for the differential equation. So if we have a differential equation, what we're going to be looking at is the slope of the curve that satisfies that equation. So we can find the slope of a solution that passes through a point by evaluating the derivative. And we know that from previous calculus, the slope is the rate of change, and so that's why we take the derivative at that point. And doing this for each point allows us to calculate the slope of any solution curve without actually finding or knowing the explicit solution. So if we can't solve for the solution explicitly, we can use this method to figure out how it behaves. So for example, consider the logistic equation for the population P, that's going to be in thousands, at time t of a certain species, and we have this given by the derivative of P with respect to t is P times 2 minus P. So just real quick, if you think about the derivative here, it's saying the rate of change of the population with respect to time. And we want to answer a few questions. Can a population of 1,000 ever decline to 500? Can the population of 1,000 ever increase to 3,000? And if the initial population is 3,000, what's the limit of the population function as t approaches infinity? Okay, so we have a differential equation. We don't have the explicit solution, but we're going to see how this would behave. Okay, so what we're going to do is we're going to draw a direction field. So we can do that by, there's online technology that can do this for us, but we're going to kind of do it by hand here by just doing a table. Think of this as like an XY table, but we have t as an input, p as an input, and then we want our slope here, which is the derivative of p with respect to t. So if we have just the population staying at 1 or 1,000, we know that t can go from 1 to 2 all the way to just any t value. So if we plug into our derivative formula here, notice the only number we actually need to plug in is p. So even though t time is changing, when p is 1, we're going to plug in here and get that the derivative is 2. And then if we change to a new p value, let's say p is 2, the derivative would be 0. And then just picking different p values, when p is 3, we're going to get the derivative as -3. When p is 4, we're going to get the derivative as -8. And so if we plot these points and draw little line segments, notice what we get. This is a direction field. And so just sort of plotting a couple of things so you can understand how this drawing came to be. Let's say we plug in 1, 1 with a slope of 2. So we find the point, 1, 1, which is right here. And the slope of the line segment at that point would be a slope of 2. So it's rising at a rate of 2 and like running with a rate of 1. And so that's why this line is rising to the right. Let's pick another one. At the point 2, 2, the slope is 0. So 2, 2, which should be right here. Notice our little line segment has a slope of 0. It's a horizontal line. And then let's just pick one more. Let's do 1, 4. So 1, 4 is right here. And notice the slope is going down pretty steeply. So it is the slope of -8 right there. It's a little line segment with a slope that's going down steep to the right. So it's representing the -8. So that's our direction field, kind of doing it by hand by plugging in values and getting the slope at points. And so let's answer our questions. Notice the direction field shows that populations under 2,000 steadily increase. So here's 2,000, and based on our direction field, all these populations are growing. Notice the slopes. They're going up toward the right. So populations are increasing under 2,000. And so the question was, can a population of 1,000 ever decline to 500? No, because anything at 1,000, notice it's here, they're all growing. So they're not going to decrease based on this direction field. For the next question, as time progresses, populations above 2,000 decrease. So again, here's 2,000, and all the populations above that, notice they're all decreasing. All the slopes are going down toward the right, which means they're decreasing. And so can a population of 1,000 ever increase to 3,000? The answer is no for that one, because down here, the populations are increasing, but then notice what they're approaching. They're increasing to 2,000. They're approaching 2,000. And then anything above 2,000 is decreasing to 2,000 as well. So we're not going to like jump over this asymptote to get to 3,000. And then if the initial population is 3,000, what's the limit of the population as t approaches infinity? So we know that p of 0, which is the initial time, is 3. And then the limit as t approaches infinity is 2. Okay, so p of 0 is 3, is up here. And then as we're approaching infinity for t, we are approaching 2. Okay, so just an example here, using a direction field. We never actually found the equation for population, the function, but we did figure out some behavior. And so this is actually an example of what's called an autonomous equation. And so an autonomous equation looks like this, where we have the derivative equals y prime equals f of y, and the right side is a function of the dependent variable only, and then the slopes are the same along each horizontal line. So if you notice, if you just pick a place, like let's pick right here, right underneath 2, all the slopes are the same along that horizontal line. So that's an autonomous equation. So next we're going to talk about the method of isoclines. And so when we're hand sketching a direction field, like we just did, the method of isoclines is actually pretty helpful. So here's how this works. So for your differential equation, y prime equals a function of x and y. An isocline is just a level curve for the function f, which is a set of points where all the solutions have the same slope. And remember, the slope is just the derivative. Okay, so for example, y prime is a function of x and y, and we're going to say that it equals x plus y. So your isoclines are of the form x plus y equals some constant c. And so in order to graph this, what you can do is, since this is going to be lines, this is really nice, put it in slope-intercept form. And so y equals negative x plus c. And so this is just going to be lines with a slope of -1 at different c values. And so it looks like this. And so, for example, when c is 1, we have y equals negative x plus 1, which has a y-intercept right here. And then we go down 1 and over 1 for our slope. And we could do that for different constants. And this is our first step. So these are our lines. So next, we'll draw line segments with the slope equal to the derivative. And so the derivative was just x plus y, but that equaled c. So this equals c, and these are along our isoclines from our function for different values of c. So we had our lines, now they're dashed, but at different points, we're going to use the derivative, which in our case, if we take, for example, 1, 1, so at this point, the derivative here of our function would be 1 plus 1, because that's our two values for x and y, and the derivative is already given, and that's our slope. So this has a slope of 2 right here. Let's pick another point. Let's say right here. So based on the drawing, notice this is a horizontal line, so we should get 0 here. So this looks like, this might be at -2, +2. So if we plug that in here for our derivative, -2 plus 2 is 0. So that's our slope at that point. We can do that for all the points, all of various points. And then what we do last is we just draw some curves following our slopes. So this is a method for doing this by hand. Of course, technology exists for us to not have to do this by hand. But from here, what we could do, for example, if we draw one of these, let's draw this curve right here. So let's see if we can do that. Okay, so following it up here, we would say, okay, I'm going to draw a curve that has the slopes given by my line segments. And notice these are all actually just going down to the right. So that's this one. And then let's try another one. So let's see if we can get this one here. So we start drawing curve that has the same slope as our little line segments. And then, so notice we have to have a slope that's going horizontal right here. So then our curve slopes to have horizontal slope right there. And then it's going to curve upward. Okay. And so we have it curving upward and like that. So I actually drew something a little different. I drew the one right above here. And so you can do that for just different locations on your XY plane. And that's how you can get some solution curves without actually explicitly solving for them. All right, so this was it for direction fields. Thanks for watching.